Let's look at the series generated by the summation c sub n times the quantity x minus a, where the quantity is raised to the n, as n goes from 0 to infinity. If we expand the binomial, we will see that the first term is c sub 0 times 1. Remember, any quantity, as long as that quantity is not 0, raised to the 0 will be 1, plus c sub 1 times the quantity x minus a, plus c sub 2 times the quantity x minus a quantity squared, and so on. This is called a power series, and this power series has coefficients c sub 0, c sub 1, c sub 2, c sub 3, and so on. And it is centered at a, which is determined right here in the problem. Sometimes when you read a problem, they might say this series is about a. It means the same thing. Now, the radius of convergence r is very similar to a geometric series. We know that the absolute value of x minus a, when it's less than this radius, will converge absolutely. Just as we know that the absolute value of x minus a being greater than r will diverge. But the problem is we don't know exactly what is going on with these coefficients. And since we can no longer guarantee that this is a geometric series, we're not sure exactly what's going to happen at the endpoints. So this leads us to one of four possibilities for the interval of convergence. Does the interval of convergence contain neither the left or right endpoint? Maybe it only contains the left. Maybe it only contains the right. Maybe it contains both endpoints. This is what we need to determine. To determine the radius of convergence, we're likely to use the ratio test and occasionally the root test. Now, the ratio test helps us determine what essentially is happening as we go from term to successive term. Again, we can't guarantee that this is going to be a geometric series. But the ratio and root tests are not helpful when we're determining the endpoints because we would get back inconclusive results. This is best demonstrated by the numerous examples to follow. The first example will be the summation as x raised to the n over n squared as n goes from 1 to infinity. Let's plug in the different values of n and expand the series so it becomes x plus 1/4 x squared plus 1/9 x cubed, and so on. The series does not share a common ratio and therefore is not geometric. So in order to determine the radius and interval of convergence, we will need to use the ratio test. The ratio test is when you take the limit as n approaches infinity of the absolute value in which the successive term is being divided by the original term. If I was to rewrite it so that I am actually multiplying by the reciprocal of the denominator, I would probably want to combine the terms so that n squared and n plus 1 quantities squared are together and x to the n plus 1 over x to the n are together. For the first piece, I want to take the x to the n plus 1 over x to the n and realize that I come up with the value of x. Now, as I focus on the limit that involves the n, I take n squared over n plus 1 quantity squared, probably should expand the binomial out, realize that I have the same degree, both 2 here and here. I also have the same coefficient, 1, in front of that term, and I can come up with the limit to being equal 1, which when multiplied to the absolute value of x gives me the absolute value of x. Now the ratio test says that I will converge if my values of x are less than 1. This determines the interval of convergence. It says it's between -1 and 1. What it does not say is what's happening at the endpoints. But before I get to there, let's look at a graphic in which I plot 1 and I plot -1. I'm going to put big giant circles here. And the reason I'm putting big giant circles here is I don't know what's happening at these endpoints quite yet. But what I do know is everything in between there is going to converge. That is why this is the interval of convergence. Now, if I was to find the center of this particular spot, I'd probably find the center to be at 0. I can determine that by going all the way back to here, realizing that x to the n is actually the same as the quantity of x minus 0, that quantity raised to the n. This determines my center. So, in the end, I can conclude that my radius of convergence is 1 because the distance between 0 and 1 is 1, and the distance between 0 and negative 1 is 1, and it was occurring with the center at 0. In order to determine which endpoints are to be included or not to be included in the interval of convergence, we will need to test the values at each of the endpoints. So let's start with the left endpoint of x equaling negative 1. If I was to plug negative 1 into the x in the summation above, I would get a new summation of negative 1 raised to the n over n squared as n goes from 1 to infinity. By expanding it out, I would come up with an alternating series of negative 1 plus 1/4 minus 1/9 plus 1/16, and so on. Now, I can run the alternating series test, and it will meet all the conditions to show that this series will converge specifically at negative 1. Therefore, the left endpoint at negative 1 needs to be included as part of the interval of convergence. I will do the same thing with the right endpoint now, where I plug 1 into the original summation. This will produce a summation of 1 raised to the n over n squared as n goes from 1 to infinity. Now I know that 1 raised to anything ends up being 1. So what I actually get is the summation of 1 over n squared. When I plug in its values, I will see I get 1 plus 1/4 plus 1/9 plus 1/16. But I really didn't need to do that because I can go back to here, recognize 1 over n squared as a p-series where p value was 2, and since 2 is greater than 1, we can determine that the series will also converge when x equals 1. Therefore, the right endpoint also needs to be included. So in the end, I can show that my interval of convergence falls between negative 1 and 1, in which negative 1 and 1 are both included. Example number 2 is the summation of negative 1 raised to the n times x to the n all over n plus 1 as n goes from 0 to infinity. I've expanded it out and came up with 1 minus 1/2 x plus 1/3 x squared minus 1/4 x cubed, and I can see it's an alternating series. I will look at the ratio test to help me determine. But when I plug in my successive term and my original term, I have no reason to include the negative 1 because negative 1 raised to the n is irrelevant when it comes to an absolute value. So I've now rewritten my ratio test so that I can combine my terms n plus 1 over n plus 2 and x to the n plus 1 over x to the n. Since I've done a lot of this work in the first example, we can determine very quickly that my limit ends up being the absolute value of 1x again, which is the same as the absolute value of x. So again, the interval of convergence will occur when the absolute value of x is less than 1. Again, this falls between negative 1 and 1. I can determine again my radius of convergence is 1 at a center of 0. So let's determine which endpoints will be included or not included in the interval of convergence by again starting with negative 1, the left endpoint. If we plug it into the formula, your numerator now goes negative 1 to the n times negative 1 to the n. Now if I were to simplify that, I would actually be getting 1 to the n, as we know, equals 1. And if I was to expand that series, I'd be coming up with 1/2 plus 1/3 plus 1/4 plus 1/5. You might recognize it immediately as a harmonic series, just with the missing term of 1 over 1. If you don't, you could also limit compare it to that harmonic series 1 over n. And in both cases, it will diverge. Therefore, the left endpoint negative 1 should not be included in the interval. On the other hand, if you plug in x equals 1 into the original formula, you will see that 1 to the n is essentially 1, which multiplied to negative 1 to the n produces just negative 1 to the n. So if I was to expand this particular series, I would start off with 1/2, then I'd subtract 1/3 plus 1/4, and I would have essentially an alternating harmonic series, which we know converges. Therefore, the right endpoint would be 1. And that tells me that the interval of convergence for this example number 2 is negative 1 is less than x, which is less than or equal to 1. For this third example, I am looking for an interval of convergence whose center is not at 0. So we will study the summation of the quantity x minus 5 raised to the n all over 2 to the n times n, as n goes from 1 to infinity. By expanding out the series, we get some very unique denominators. By applying the ratio test and going through the process and simplifying the work, we will find out we have 3 fractions that we probably want to study. Focusing on the last 2 right here, we will realize that x minus 5 to the n plus 1 over x minus 5 quantity raised to the n will leave just an x minus 5 in the numerator. But having 2 to the n over 2 to the n plus 1 is going to leave a 2 in the denominator, leaving us with this limit. Now, by focusing on the limit as n approaches infinity of n over n plus 1, that essentially is 1, so 1 times my x minus 5 over 2, when put in the absolute value, will be the value which needs to be less than 1 to produce my interval of convergence. So what does that mean? Well, if we look at negative 1 being less than x minus 5 all over 2, which is less than 1, we can multiply both sides by 2 and then add 5. And that will become our interval of convergence between 3 and 7. Now, that tells me that my radius of convergence is 2 with the center of 5. Again, let's go back to the original summation right here. We said that x minus a raised to the n, a is going to be your center. Since this is x minus 5, a must be 5. And since 5 is 2 away from both 3 and 7, that is why my radius of convergence is 2. Even though its interval of convergence does not have a center of 0, but 5, we still need to determine what's happening at the endpoints. So let's start with x equals 3. Plugging it into the summation, the numerator's quantity 3 minus 5 will simplify to negative 2 quantity raised to the n. This is being divided by 2 to the n, and so we could rewrite this as negative 1 to the n all over n. As a series, this becomes an alternating harmonic series, and as we know, converges. Therefore, the left endpoint 3 would be included. Plugging in 7 to the same summation and getting the quantity 7 minus 5 on top, we would get 2 to the n on top, 2 to the n on bottom. This cancels out simply to 1 over n. 1 over n is a harmonic series, which diverges. Therefore, the right endpoint should not be included. And you will get an interval of convergence where 3 is less than or equal to x, which is less than or equal to 7. Example number 4 is the summation of negative 1 raised to the n times x raised to the 2n minus 1, all being divided by a quantity of 2n minus 1 factorial as n goes from 1 to infinity. As you expand out the series, you might be inclined to evaluate the different factorials. I don't know if I would recommend this, as it's easier to see a pattern of 1 factorial, 3 factorial, 5 factorial, 7 factorial than it is to see denominators of 1, 6, 120, and 50, 40. Now, because of those factorials, we definitely want to apply the ratio test. And as we apply the ratio test, be very careful on how you plug the n plus 1 in, especially in this problem, because we will need to apply 2 to that quantity before we subtract the 1. And not only do we do this once, we do this twice in this particular problem. For instance, we'll now have limit as n approaches infinity of the absolute value of x raised to the 2n plus 1 being divided by the quantity 2n plus 1 factorial, being multiplied now by the denominator's reciprocal, quantity 2n minus 1 factorial all over x to the 2n minus 1. As we continue simplifying the process, you will want to remember, what does it mean to be 2n plus 1 quantity factorial? So 2n plus 1 quantity factorial is you saying 2n plus 1 times 2n times 2n minus 1 times 2n minus 2 and 2n minus 3, so on until you get down to 1, which we can just take those terms starting at 2n minus 1 and write it as a factorial. And that's helpful because then we can cancel out those particular pieces. And we'll come up with 1 over 2n plus 1 times 2n. Now, when you simplify x to the 2n plus 1 over x to the 2n minus 1, you get x squared. Now, you might think this has some relevance, but in this particular case it does not, because when we actually examine what happens here with the limit as n approaches infinity, you will realize that our degree on top is 0, but our degree in the denominator is second. And therefore, what's going to produce is a limit of 0. And 0 times x squared is going to produce a value of 0. Now remember, the interval of convergence is any time a value of x is less than 1. But in this case, we're saying no matter what x should come up with, it always equals 0. Therefore, our radius is actually infinite. There is no reason to check the endpoints because literally our interval of convergence is every real number there is, from negative infinity all the way to infinity, because 0, which we established as our limit, is always going to be less than 1. X is irrelevant in this particular problem. The next example is the summation of n to the n times x to the n as n goes from 1 to infinity. As we expand out the series, we can rewrite it as x plus 4x squared plus 27x cubed plus 256x to the fourth, and so on. But going back to our original summation, I see n to the n, x to the n. This is an excellent time to use the root test over the ratio test. And so I'll set up a limit as n approaches infinity of the nth root of the absolute value of n to the n, x to the n. This will equal the limit as n approaches infinity of the absolute value of nx. As long as x is a non-zero number, I have to remember that n is going to be increasing without bound. So I could say that my limit should be infinity. Now, since infinity really is never less than 1, we're going to run into some issues. The only way for this series to converge is if we actually had x originally be 0. Let me show you what happens if I plug in 0 into the summation. As I expand out the different terms, each term will produce a value of 0, which equals 0. So by definition, it is converging to 0. Therefore, in this particular problem, the radius of convergence is 0, literally a single point, who happens to be the center of 0. And therefore, there is no reason to check endpoints because the endpoint is 0, and my interval convergence is the single number 0. Let's look at an alternate version of the problem we just did. In this case, n to the n will now be multiplied to the quantity x plus 2 raised to the n. We will again apply the root test, and as we go through the process of determining the limit, we should come to the same conclusion as before. Our limit is infinity. And because we have the same situation, the only way we'll get this to converge is if this time x plus 2 equals 0, which means we will need to use a value of x equal negative 2 in the summation to produce the n to the n times 0 raised to the n. And this will produce terms that are all 0 so that we can come up with a sum that equals 0. So in the end, our radius of convergence is 0, a single point. Its center is at negative 2. We don't need to worry about endpoints because our interval of convergence is the value negative 2.